Good morning, everybody. So today we are going to carry on with what we started disastrously yesterday, because I was really struggling with my eyes, and so it was very difficult for me to maintain my attention and even to look at the screen in front of me and look at my notes and stuff. It was really hard, and my apologies for yesterday, but I've been dealing with problems with my eyes now for about 3 weeks, and today I will say that my eyes are feeling about 75%, and yesterday morning they felt awful. So I think I'm on the upswing finally. So what I have done today is I have posted onto Brightspace study notes for this chapter 14, B1 chapter 14. There's about 5 pages that kind of goes over, well, it goes over the stuff we were going over yesterday with regard to procedure qualification and performance qualification. Now, if you're wondering where on earth did this guy pull this out of his hiney, and why did he subject us to welding procedure qualification and welder performance qualification, I just want you to know that my plan of attack for chapter 14 is to go backwards. And so we started on objective 8. The next thing we do is we'll go on to objective 7 and blah, blah, blah. Because I think if we start with weld procedures and welder performance qualifications, we introduce all of the concepts that are everywhere else in the chapter, and then also we can then put all of the stuff that's in the rest of the chapter into its proper context. Basically, the stuff in the chapter all fits within the idea of procedure qualification and performance qualification. And you'll notice if you look at the chapter questions in the back of chapter 14, question number 7 is describe the following terms. Welding procedure qualification. Well, you know what welding procedure qualification is all about. It means you have to make a weld procedure specification, then you got to have evidence that the weld procedure works, which is the procedure qualification record. And the other part of question 7 says, define welder performance qualification. And so then that's what we started off, and I think we kind of ended off there. But welder performance qualification, basically, we've got a welder that welds to a procedure. And the welder must prove that he or she is competent at welding a particular procedure before doing an actual production weld. They can practice all day long, and a lot of weld shops permit the welders to practice, give them an hour or 2 hours every day for a week, so they practice a procedure before they actually go to the weld test center and actually do the test so that they'll pass the test. But what we're going to talk about today a little bit is about the myriad of possible procedures and how ASME Code Section 9 deals with the fact that, there's no way that a welder can be qualified in every possible weld procedure, because, they're only limited by the imagination of people who want to stick metal together, So we're going to finish that off today. And then we're going to get into non-destructive examination, and of course we've done a big chunk of that. We did our little jigsaw thing, and people did work in groups, and they reported on different types of non-destructive examination. So what we're going to do is look at NDE then, not from the same perspective, in other words, well, how does UT work and how does RT work and blah blah blah, but no, we're going to look at it from the perspective of someone who does non-destructive examination. What exactly is the procedure that they follow? Because we know that there are lots of tools that are in the tool belt of the non-destructive examination technicians. And we've looked at those 4 already. So now, what does that technician do when they're doing an actual test, when they're doing an actual examination? at some point, they've got to be able to identify a problem, and then they have to be able to recognize what that problem is, and then they have to do some kind of evaluation. Is this a big problem, or is this something that we can live with? So this is the type of stuff we're going to look at when it comes to non-destructive examination. As for weld defects, we're not going to really spend a lot of time on that. It's the kind of thing that you can read over yourself, but basically we've got two main categories of weld defects. One of them is dimensional in aspect, and the other one is what we call a discontinuity. So we'll take a look at both of those things and see what that means to have a discontinuity or to have a dimensional defect. And I hope that we'll get finished heat treatment today, which you're going to find is all about metallurgy. So back when we were covering metallurgy, we looked at different unit cell structures. So we had ferrite, pearlite, austenite, and so ferrite and pearlite were body-centered cubic, and austenite is face-centered cubic. And then we had this thing called martensite, which was body-centered tetragonal, and we learned that steel could change its, or iron could change its unit cell structure. It depends upon its temperature and also on its rate of cooling. And so that's where all of this heat treatment stuff comes in. And so we're going to take that iron-carbon phase diagram and we're going to relate it to the heat treatment processes that are covered in your textbook. That's what our day looks like. And maybe if we're really lucky, we'll get into welding processes, but I kind of doubt that we're going to get that far. So we had weld procedure specification, and that weld procedure specification is the recipe for making the weld. And so what we have to do then is qualify the procedure to make sure it's a good weld. And so what we end up with is evidence of a good weld procedure is a procedure qualification record. Procedure qualification record. Now, one thing that I didn't mention yesterday is once that weld procedure is qualified and you've got a PQR, then you have to submit that into the jurisdiction and get a Canadian registration number. And you know what CRNs are, right? But did you know that every qualified weld procedure in Canada has to have a CRN? So it's not just enough to have a good weld procedure. It's not good enough to have a procedure qualification record. You have to send it off to ABSA or whoever the authority is in BC or Saskatchewan or Manitoba. You have to send in that weld procedure and you're going to get a CRN. So you have to have a CRN to do a weld procedure in the province of Alberta. And that would come from ABSA. So now we've got a qualified weld procedure. Now we need qualified welders. And so we said, by the way, this here is all procedure qualification. And this, by the way, is what we call it in ASME Section 9. But now what we have to have is welder performance qualification, which is WPQ. And so this means can the welder follow the recipe? And if they follow the WPS, are they skilled enough to produce a strong and ductile weld that they know the procedure can make? So can the welder reproduce? We're going to call it reproduce because this is all reproducibility. reproduce the strong ductile weld. If they can, then the welder gets a license. And the license permits them to do the weld that's in the procedure. So if we have got, 10,000 different materials that can possibly be welded together, and if we've got, 4 different weld positions, and if we've got, and on and on and on, different processes, and, laser beam welding and whatever, there is an infinite number of possible weld licenses that a welder can get, because there is an infinite number of weld procedures. So there are these things that are called standard weld procedures. And this, I'm not sure if this is in the code section 9, but if you Google this, standard weld procedures, you're going to find that there are certain procedures that cover the most common materials and using the most common processes. So the most common process is probably shielded metal arc welding, or arc welding, or stick welding we call it. It's pretty common. And it's very common to use an F3 electrode, which is an E6010 electrode. It's also very, very common to use an F4 electrode, which is an E7018 grouping. The first two numbers are thousands of psi tensile strength. The third number there represents the position, so that would mean all position. 1 means all position. It means you can use that rod overhead, you can use it horizontal, vertical, whatever. And then the last number refers to the characteristics of the coating and maybe the characteristic of the rod. Can you use it for AC? Can you use it only for DC? Can you use it for DC straight? Can you use it for DC reverse? Can you use it for both? Can you use it for all of them? What kind of slag does it make? Does it make a glassy slag? Does it make a light slag? All this kind of stuff. So there's a lot of information in that last number, and you really don't need to know what all that information is. All you need to know is that there's a number there, and you can look it up, you can go online, you can figure out what that last number means. Need to know basis. So that's one of the things we're going to have on the so-called standard weld procedure. Then the next thing we're going to do is it's going to be pipe. And the reason it'll be pipe is because pipe is hard to weld. It's much harder to weld than flat plate. So if you can do a hard weld, you can automatically qualify to do an easy weld. So if I can weld on pipe, and I demonstrate during my test that I do a nice weld on pipe, then I am automatically qualified to weld the same material groupings on plate. Then we're going to have position. And what we would like our welders to do is to weld in all positions. So, okay, here is a weld plate. And here's the same plate, but a side view. Okay, if I am looking down, let me put my eyeball here, okay? And I should put blood on it or something like that. It should be dripping blood, my poor eyeball. So my eyeball is looking down, and it's like a tabletop. And here's my welding electrode. And I'll give you a sound effect. And my arc is going on there, and I'm making a weld deposit. We call that the flat position. And that's super easy. We call that actually position number 1. Position number 1 is super easy. Now, this one here in front of me is the wall in front of my face. And I've got a groove joint that goes from my left to the right. And then I'm going to take an electrode and I can go zzz, 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 zzz. That is position number 2, which is horizontal. Okay. Now, let's say I'm looking at the wall in front of me and I'm going to go from my feet to my head. Zzz, 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 zzz. That is vertical. That's position number 5. Vertical. And I can also weld overhead. Okay, and so if I'm going to be welding pipe, what I'm going to do is weld, let's say, an NPS 4 pipe that is sked 80 or maybe sked 40. And so it's going to have a groove. Okay, so this is going to be a groove weld. And the first thing I'm going to do is, well, I'm going to mark it into thirds. 1/3, 1/3, 1/3. And the third that you're looking at right now, I'm going to weld it in the position number 2, horizontal. Because it's a groove weld, we call that the 2G position. 2 meaning horizontal, G meaning it's a groove weld. And then what I'm going to do is I'm going to reposition that thing. After I complete that weld, I'm going to put the pipe like this. And I've already welded this part here. I've already welded the top third of it in the 2G position. Now I'm going to start here on the bottom. And this pipe is actually going to be over my head. And I'm going to weld it this way. Zzz, 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 zzz. And then I'm going to do the other side of it as well. Zzz, 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 zzz. So that's the vertical, but actually right here at the bottom, it's also overhead. So we call that the 5G position. In other words, it's position number 5, vertical, and it's G for a groove weld. Then what's going to happen is the examiner is going to cut it up into pieces, and they're going to do all of the destructive and non-destructive examination. And if I pass, the license that I get is going to be a 2G, 5G weld. And that says that I can weld in those positions. And a 2G, 5G is an all, where are we? An all, come on, what happened to my pen? Again, I'm having trouble. A 2G, 5G is an all position weld. Once I've passed my weld test, I can do subsequent tests with my pipe located on a 45-degree angle. And if it's on a 45-degree angle, we call that the 6G position. So after I do the 2G and the 5G, then what I can do is I can take my pipe. Ooh, it drives me crazy. This one. Drag that over here. Enough of that nonsense. So now I'm going to position it at a 45-degree angle. And I'm going to start at the bottom, and I'm going to go zzz, 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 weld it all the way to the top. And then I'm going to go to the other side, zzz, 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 weld it all the way up to the top. And then what I've done is I've completed a 6G weld, which is the equivalent of a 2G, 5G. Okay, so G for groove weld. Groove welds are harder to do than fillet welds. So here is a fillet weld. This one here is a T. And first I'm going to put in a root pass. Zzz, zzz, and then I'm going to put in my subsequent passes So I'm going to fill it and cap it, and then I'm going to put in the root, and then I'm going to fill it and cap it. This one's pretty easy to use because all of this material here is called backing material, and it prevents burn through. So you can be a little sloppy with your heat. You can have too much heat, and it won't have too much of an effect because you have all of that backing material preventing burn through. Well, these G welds here are hard to do because I'm going to prepare my pipe. Remember, I want to weld it on pipe because it qualifies me for plate. And then I'm going to weld to what's called an open root, which is hard. It's hard to do this, but this is pressure welders weld to. They weld to an open root. They don't test with backing material. And if I can lay down a good root pass, and then I can fill it and cap it and make a good high quality weld, if I can do all that to an open root, that automatically qualifies me for any weld that requires a backing ring or a backing plate or any fillet weld in any position. So we said that, say, 2G, 5G is an all-position groove weld. There is something called a 2F, which is a horizontal fillet weld, and there's a 5F, which is a vertical fillet weld. Okay, so those are fillet welds, but those ones are easy to do. So if I go to the Weld Test Center and I say I want to do a 2F and a 5F on plate, the weld examiner would scratch his head and go, gee, I don't know, do you really want to do that? Because it really limits to what you can do. You can't weld pipe if you're going to test on plate, and you can't do groove welds if you're going to do fillet weld test. Maybe that's all the company's going to send you for. But what a company really wants you to do is have an all-position groove weld because it qualifies you to do fillet welds in all positions. And they want you to work on pipe because it also allows you to weld plate. Now, so what did we look at so far? We said we want an all-position weld, an all-position certificate. We want it done on pipe. We wanted, I can't remember what was on that other slide. The most common materials are going to be P1 materials, which are low carbon steel. And so a P1 to P1 means that I'm going to say, take this plate here, which is a P1 material, and another plate, which is another P1 material. And because most of the materials that we weld are P1 materials, we don't need any kind of extra special procedure. Ultimately, we end up with a I don't think I talked about, did I talk about F3, F4? I can't remember. Those are the different electrodes. So typically we do is an F3 root and an F4 fill and cap. And the reason for this is an F3 rod is really easy to get to the root, whereas an F4 is very difficult to get to the root, and it's because of the type of coating that's on the electrode. The coating is kind of big and bulky on an F4 electrode, so it's really hard to lay down a good root pass. So what they're going to do is test using an F3 E6010 electrode to the root and an F4 E7018 electrode for the fill and cap. Okay, all positions, so that would be 2G, 5G, or 6G. P1 P1 to P1 on pipe of a particular diameter and a particular thickness range. And so when the welder qualifies for this test, that means that he or she can do maybe 80 to 90% of all welds that the company does. Makes sense? So even though there's a myriad of materials that we can weld, even though there's different processes that we can follow, using SMEW and those electrodes to weld low carbon steel, pipe and all position, that's most of what companies do. So that's what they send their welders to test for. So we did say that there's multiple weld procedures. This would be specified in the weld procedure specification. All of it's in the WPS, and then the welder is free to weld 80 to 90% of the work that the company engages in. As I said, we're going to get into non-destructive examination. And of course, there's destructive and non-destructive, and destructive is, kind of limited to specific lab procedures, because, we don't want to destructively, examine a completed boiler. Well, let's see how strong your boiler welds are. So we're going to take your boiler shell and we're going to put it inside of a concrete abutment, and we're going to raise it to 8 times the maximum level working pressure and explode the thing and go, yeah, them were some pretty good welds. Do it again. We're not going to do that. So we are going to inspect welds after they have been done to determine if they're okay. And of course, we've got things like visual penetrant testing, which can be a fluorescent dye or a visible dye. We can also do magnetic particle testing. And the magnetic particle testing, some of you saw them doing it on the deaerator in the not Johnson Cobb building, but the Thomas Riley building. Okay, and we know that each one of these has pros and cons. So for example, the mag particle testing can only be done on ferrous materials, so it has to be something that we can magnetize. You can't use it on plastic, you can't use it on wood, you can't use it on aluminum or copper. It has to be ferrous material. As for fluorescent visible dye penetrant, all we can find there are indications that come to the surface. So if it's porosity, if it's visible at the surface, we can pick it up. Or if it's a crack that we can see that it extends to the surface, we can pick it up. But anything that is inside the material, we're going to have to use what's called volumetric testing. And by volume, we mean length times width times height, right? So, in other words, it's a test that examines the entire volume of material. And volumetric testing includes 2 very important ones: ultrasonic testing, where we pass a sound wave through the material and we have reflectors and anything that's a discontinuity inside of the material that reflects the ultrasonic sound, we can pick it up by how fast the sound reflects. And then of course we've got the X-rays, the radiographic testing, and we can either have gamma radiation, or we can have actual X-rays being used. And so then the good thing about these is we can find subsurface indications. indication. I've used some technical terminology. What is an indication? What do we mean by the word indication? Any guesses?
Any gas or excess material?
Okay, so I get. What was the last thing you said?
Like foreign material, like defects in the piece, I guess.
Okay, so it could be foreign material, it could be a gap of some sort. An indication then is really, really vague. Indication is simply, what do you see? It's something. I'm going to put that in quotation marks. It's something. I see something. Well, what is it? I don't know what it is, but it's something. It's there. How do you know it's there? Well, I saw it. Oh, okay. So that is what an indication is. It's just something that you see. That's it. Then the next thing that we have to do is interpret. Once we have an indication, we got to figure out what is it. This is when we can start to be specific. So we might have things like a crack, yes. We might have porosity, which are little bubbles. We might have pieces of slag from the welding process. We call that a slag inclusion. What else might we have in there? Slag inclusions, cracks, bubbles. Okay, so we've made an interpretation, and we've figured out what it is. And then what we're going to have to do is determine, as part of the interpretation, is it false? Is it non-relevant? Or is it relevant? So as for the false one, let's take a look at this one first. We know that visible dye penetrant isn't good on rough surfaces because you've got a lot of non-relevant indications. On a rough surface, you're going to see all of this red stuff. And even though you've cleaned it and even though you've applied developer, the rough surface tends to gather little bits of dye penetrant, so when you spray the developer on, you're going to see lots of red, and then you're going to go, oh, am I looking at pores? Is this porosity? Am I looking at, what is it that I'm looking at? I have an indication. There could be something seriously wrong, but then as part of the interpretation you go, guess what? It's a rough casting, and this isn't the best method for inspecting a rough casting, and all those indications that I saw, all that sea of red, doesn't mean anything. So that would be the case of a false indication. So we can see irrelevant noise, and noise is, you know, you're trying to listen to the radio and all you get is crackle. Okay, it's not relevant to the music. It's just signal noise. And in the case of visual testing, if we have a rough casting and we're looking for porosity, it's probably not the best method to use because we're going to get a lot of false signals. We're going to get a lot of noise. Now, let's see. A non-relevant indication. What would be a non-relevant indication? Well, basically this is not important. So let's say I'm using radiographic testing of a weld, and there's my groove weld, and normally my weld shouldn't have a lot of reinforcement. A little bit of reinforcement is okay, but usually shouldn't be a lot. But let's say this weld had a lot of reinforcement. Well, on my radiographic image, I'm going to show sort of this whitish bubble on the top, and it's going to be whiter because more radiation is absorbed through that increased thickness. So that little whitish area, we're going to go, what is that? And then we're going to interpret it, and we're going to go, oh, it's excess reinforcement. And then you say, well, is it relevant or is it irrelevant? Nah, it's non-relevant. It doesn't affect the quality of this weld. So there's an example of a non-relevant indication. But the relevant indication is the one that we really want to find. The relevant indication is, a crack. And it went all the way to the surface of the material. That's a problem. So what we're going to do to determine relevancy is we need a set of acceptance criteria. And really what I should do is kind of put down the next step. If we've got a relevant indication, then we need to evaluate this indication. So how do we evaluate it? Well, we've got a set of acceptance criteria. And the acceptance criteria might say, any crack that is greater than 1/16 of an inch in length is rejectable. Or it might say any undercut in excess of 1/32 of an inch is unacceptable. Or it'll say any cluster porosity greater than so many clusters within so much length of a weld is unacceptable. So here we have to go to a code book like ASME Code Section 5, which is the non-destructive examination, which talks about the procedure that we follow during NDE. And then what we're going to do is go to ASME 1, ASME 8, or whatever the code happens to be, the code of construction, and they're going to say what's acceptable and what's not acceptable. If I evaluate and go, yeah, there's a crack there, but it's not a bad crack, it's a teeny tiny crack and we can live with it, then we call it a flaw. Flaws are acceptable. They pass the test. Maybe you only got 60% on the test, but it's still a pass. Let me put it this way. If it's a nuclear code, no, it wouldn't pass. But if it's just a regular boiler code, yeah, it'll pass. Okay? Or if it's a real baddie, then what we have is called a defect. A defect then is a relevant, unacceptable indication. But we had to go a little ways before we got there. Okay, before we could identify something as being a defect, we had to first of all identify it as an indication. Okay, we had to see it first. And to see it, we used non-destructive examination. Then we had to interpret, what is it? Is it a slag inclusion or is it a bubble? Is it noise? So is it a false indication? Is it a non-relevant indication? Or is it a relevant indication? And then the next step is, if it is in fact a relevant indication, can we live with it? Then it's just called a flaw. Or if it's absolutely unacceptable, it's a defect, and we have to reject it. So any idea what we do if there's a defect in a weld? Like, what do we do? So they're welding up a boiler, and the National Board Inspector shows up at the shop and says, oh, you've got some weld defects here, 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 and here. What do?
Could you actually re-weld that, or would you have to just get like a new boiler?
Okay, so that's option A would be, they've welded up the boiler shell and they've spent $80,000 on materials and $60,000 on labor and $5,000 on non-destructive examination. And then the inspector comes along and says, the shell's no good, throw it out. Well, maybe they can cut it in half and use it for making an animal feeder, but they likely would not do that because they got a lot of money invested in it. So what's option B? If they're not going to throw out the vessel or turn it into a hog trough, what's the next option?
You can clean out the weld and then re-weld.
Bingo. Yeah, you got to remove the weld. So they'll take a grinder or they'll take a gouger or something like that, and they're going to gouge out the weld. They're going to remove the weld. They're going to remove the defective part, and they're going to redo it. And then they're going to re-inspect it, and hopefully it'll pass the second time. Okay, so finding a defect, this is what the process is all about. Find and repair defects before it leaves the factory. And of course, we apply the same stuff to repairs in the field. So factory, during production, we've got non-destructive examination, or field repairs. Again, we want to make sure that the welds are high quality.